Alright, today guys I'm gonna be solving a circuit problem, so it's gonna be pretty scuffed, I'm sorry, but I'm gonna walk you through it anyways. So I'm gonna flip you around, I'm gonna turn this on really fast. Get everything set up. Whoop. Alright. Alright. This should be good, guys. I'm gonna raise this a little bit. Come on. Alright, so we're going to be doing a non-ideal. Here's the values for the circuit. It's going to look like this. By the way, this problem, I did it, and I have a PhD professor who I had checked my work. So, yeah. But I'm still going to, I did this problem a while ago, but I thought I'll help spread knowledge by doing it. So I'm a little shaky on things. It's my first time doing it since solving the problem, but that's okay. So this is 4K ohms. This is 16K. ohms. Sorry about the handwriting. This is 16. Oh, I'll make it a little better. I'm sorry. I'll extend it out here. 16K ohms. Then we're gonna go down. It's gonna connect here, and it's gonna be V out. So first, we have to find the okay. Sorry, we have to find the expression for the closed loop gain. That's number A, as a function of S. So now, going back to my notes, the equation for that is AF equals GAB 1 plus B naught. Sorry, is this B naught? Beta. I don't know exactly what it is, but it's the weird looking B. I'm sorry. Which equals G A beta over 1 plus A beta times 1 over 1 plus S over WP. I have it. I have it when I originally solved it up right now. Let me zoom in really fast. 1 plus. Perfect. So this is the equation. You just kind of just have to know this. So in this problem, this all just go this. Okay, I believe this S is a 0. So this all just goes to 1 over 1, which is just going to be 1. So we're going to have G A naught B over 1 plus A naught B times 1. So this we're just going to solve. We're just going to get that. All right. If you can kind of make that out. I'm sorry. I might turn it down a little bit. Maybe this will be more clear. That's a little better, I believe. Or I can't tell. I can try pen. I just hope that the pen won't. If I make a mistake, I'm sorry with the pen. But okay. So now let's go back up. Let's make the expression with R specific problem. So I'm also doing this because I haven't worked through this in like at least a month, about a month. This is also to make it so I'm gonna put things together with you so I can help explain things better. So also keep the circuit in mind, like write this down. So this is 4K, 16K. Obviously, if you don't know, when the source is into the positive, it is non-inverting, which is 1 plus RF over R1 or RN. Okay, so we have to get the G, which G is gain, so G is just gonna be 1 plus R2 over R1, which boom, 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 boom. Oops, sorry, boom, 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 boom. Okay, because this is R2, this is R1. All right, and then we need to find A and beta. Okay, so we're gonna put this all together. So we're solving this algebraically, so we're not gonna use any values, sadly. Okay, so why do I have A not there? Let me look. Oh, okay. I solve analytically with A naught and WP, so we're allowed to use those two variables. All right, and beta is R1 over R2 plus R2, which, let me think, let me go back. How did I get that? Let me think. 1 over 5. I should have figured this out really fast. 4 over. Okay, beta. According to my notes, beta is just normally like this. So I'm sorry if again I'm a little like iffy on this because I'm way past this topic, but that's okay. The beta is just naturally this, from my notes at least. So this is straight up is going to be R1 plus R1 plus R2, and then all over 1 plus. Hey, yo, it's just gonna be beta because this right here is beta, so it's just gonna be beta again. All right, so this would be number A, which is I guess I didn't even use a WP. I kind of went the long route, I believe. This is gonna be all right. This would be number A, which would be find the expression for the closed loop. Oh, I'm sorry, it's not completely in there. Find the expression for the closed loop gain as a function of S. AFS, V over VS, hint solve analytically with AO over omega P before plugging the numbers. Okay. Go back to this op amp. Please remember, I'll redraw the op amp. Let me get this out of the way. I'll redraw the op amp. For kilo ohms, 16. Oops, sorry, I moved my paper because of I was trying to get that thing in line. This is still going to be non-inverting because this is in there. Yep. Oh, sorry, this should be that. Sorry about that. Okay. Number B is, what is the value of the closed loop DC gain and closed loop bandwidth? Alright, so now we're going to use the formula from last time, alright? We're going to plug things in. So keep this in mind, we're going to plug things in. Okay. So, AF equals, oh, that'll make it easy for us. I'm going to keep this right here off to the side. Alright. Alright, so G is going to be 5. Because if you think about it, okay, so R2 over R1, 16 divided by 4 is 4. Plus 1 plus 4, because the gain of a non-inverting is 1 plus R2 over R1. So that's going to be 5. Alright, so we already know. So going from this, we just did this formula basically. Or this right here. So that's going to be 5. Alright, and then A naught, I believe. Did I already write that down? I don't actually know. Alright, let me try to figure out how did they get A naught. Dang, I have to go back. Sorry about this. I'm trying to figure out how I did this. Okay, R1 over, okay, that's going to be 4 divided by 20. 4 divided by 20 is 5. So, alright, we already know this is going to be 5, or 1 over 5. Yeah, this is, okay, so this right here is 1 over 5. That's 1 over 5. So we're going to know, so 1 over 5. A naught. Oh, I'm so sorry, guys. I did give it 500 right here. I'm like so confused. I'm like, wait, shouldn't it be given? I'm so sorry about that. I was so confused. I'm like, shouldn't it be given? And yeah, it's given. Okay. All right. So this is just gonna be 100, but you know, we'll get to that. All right. So then we're just gonna use the rest of the formula. So 1 plus, you know, same thing, which in reality is 500 over 501, which I think is 4.95. I don't have a calculator on me. I can quickly look it up to make sure I'm not lying here. Oh, I am lying. Wait a second. Okay, 500 divided by 5. 100, 101. Oh, yeah, okay. Wait, no. This is not correct. That's why. 100 divided by 101 equals 4.95. No. Okay. I don't know what I did. Okay, 500 5 times. No, it is 500. What? I'm so confused right now, guys. Oh my god, wait. I am... Okay. Just completely ignore all this. I'm so sorry. Okay, so this is going to be 100, which is going to be 500, because, you know, times 5. I completely overlooked that. Which is just going to be 101. So then I'm like, wait, what the heck? 500 divided by... Again, I'm solving this with you, so... If I make mistakes, you know, that's how it's going to be. Yep, 4.95. Okay. Alright. So now... we could put this in decibel form, which is going to be 20 log this, which I'll quickly do that to make sure I get the right value. And now I'm not making really bad mistakes. Alright, this is going to be 13.89 decibels. So this will be part of our graph. Now for the bandwidth. Let's get out new paper. Now for the bandwidth. The bandwidth formula is going to be BW equals WP times 1 plus A naught beta. I'm remembering all the variables. It's been a long time, but I'm remembering. All right, so WP. If we pull out the original note paper. Oh, I threw it on the ground. So I'm gonna pick it up. WP is 2 pi FP. And this is gonna be, you know, we already did that. We already know how to do that. So it's gonna be FP is 5K. Okay. Yep, 2P is 5K. If I remember correctly, I put that down in the givens. That's the given. Alright, you know, I'm not gonna rewrite the formula. Alright. 2 pi times 5K. This is a given. So I'm sorry. I'm gonna put this entire problem in the video title and description. But I'm going off memory right now. 1 plus, okay, we already did this part, as you guys already know. Alright, because, you know, okay. And this is going to go down to... Alright. This is going to go down to 7885397. Alright, you can check that yourself. This is 5,000. Just making sure you guys know that. And this is going to be in radians, which, I mean, you can just do that yourself. Okay. Alright. Next. Now it's time to draw the little graph. Alright. So now we're going to do, alright, I'll just first sketch it over here. Oh wait, I probably shouldn't do that yet. Okay. Okay, so this is gonna be A. This is gonna be unity. Unity is where two intersections meet. Alright. And now we're gonna make it nice and simple. If we look at the givens, the A naught. So okay, we already know A naught is 500. A naught is 500, if you remember the givens from earlier. So the logs, we're going to do 20 log 500 equals about 54. Okay. So this is the decibels. This is going to be in dB. All right. This is going to be in hertz. We'll see soon enough. Okay, so this is gonna be 54. All right. And now we're gonna do. Oh, I forgot to even say the proper. Okay, plot the magnitude response of J is a imaginary number for electrical engineers. So it's just an imaginary number, and an AF J omega with the frequency, and we have to annotate max gain and bandwidth. Okay, fair enough. All right, so then we're gonna draw this little doodad, and we're gonna take the AF, which is on the other problem, I believe, unless I'm blind, which I'm not. We're gonna take this right here and put it here, because this is gonna be AF. This is not the best tutorial, but this is my first one. A9 dB. Alright. And this, we already know, is going to be 5,000 kilohertz. Alright. What else do I have to do? Okay, let me think. What else do I have to do? A naught times FP is gonna be. I wish I brought my calculator along, but okay. Let me just. Okay, the given is 500 and FP is 5. Ooh. Okay. Type that in again really fast. Sorry, guys. It's actually 5,000. Alright. Yep, okay, this is going to be 2.5 megahertz. 2.5 megahertz. Alright? So the unity is going to be. So unity is A naught FP, which is going to be 2.5 megahertz. Okie dokie. Now I need to solve for this one, which give me 1 second. Let me think how to do this one. I can look back at my notes to get the answer, but the issue is, how did I do it? Oh wait, I'm a goofball. Wait, am I? Let me go back and look. Sorry about this. I genuinely don't know how I got. I don't know how. I'm looking back. I don't know how I got this answer, which is perfect because if I figure it out, then I'll explain it. But I have a feeling I won't. Okay, so 54. There has to be some explanation. It's straight up. It's straight up just hertz. How did I get that? I'm not quite sure, guys. I'm sorry. I can't figure out what I did. But that is straight up the answer for right there. That's okay. And then the phase plot is gonna be yep. That's everything. Now I got 100% on this problem, when clearly I knew more on the exam than now. So I'm sorry. I probably should have did this thing right after the exam. But the recap, I can show you my screen. I have to be careful because I don't want to flash my name completely. So I'm going to show you my screen, and you can look at my work from my original note. So this, I'll look at this later to see if this video is good. This is my original work, a lot neater than now. So now I'm going to put it back down. I'm gonna pull my OBS back. I'm gonna say goodbye to everyone. Sorry for the bright light. Turn it off. Alright, sorry guys. That was not the best tutorial, but hope you guys learned something. If you had the same problem, I mean, I walked you through kind of how to do it. The premise, I showed you my my original work. So yeah, thanks for watching. If you went to the end, I mean, thank you. That was not the best one, but all right. Talk to you guys later. Bye.